The subject I'm going to talk about today is here. This is the nice, responsible name for this talk. It's a subject I talk a lot about, and generally just understanding and thinking about response time and latency and behavior of those things and what we should care about, what mistakes we might be doing commonly when we look at them, is the subjects that we're going to cover today. But I have multiple names for this talk. It's a subject I talk about a lot. I do talks anywhere from half an hour to 8 hours on this, sometimes in seminars. The other popular name for this is here, how not to measure latency. Sorry. And that's because a lot of what I will talk about is bad news. It's the things that we do wrong and maybe things that you learn not to do. But since I've been talking about this subject a lot, and I usually see the audience's faces when I speak about this, I've noticed a very interesting effect. At some point during this talk, some of you are going to have a oh shit moment. It looks like this. I think we do that. I think that's what I've been doing. I think this is wrong. And it's okay. We all do that. And as a rule for this talk, regardless of whether or not you feel comfortable or polite or not saying this, it is okay to say, oh shit, in the middle of this talk. Any one of you can do that. There are places, if you see something and you recognize it and you say, oh, yeah, we do that, then say, oh shit, it helps. I'll give you a few cues and I'll tell you in a couple places. But I've learned that this is a natural reaction to what I say, and that makes it fun. So let me talk a little bit about me. I'm Gil Tene. I'm the CTO of Azul Systems. At Azul, we work in Java virtual machines. We make JVMs. It's all that we do. We think we make the best JVMs on earth, obviously. I've worked on a lot of things around Java virtual machines, but probably the best known is garbage collection. We solved garbage collection. It's done. You don't have to worry about it. It just works. Everything's nice and smooth, etc. Right? And the way we dealt with it is really to take a complete different approach to what the problem is, what we want to solve, how we would solve it, and kind of fix it. People still often don't believe me when I say that, so I have to show them. And how do I show them? I have to measure latency and response time. And I run into all these ways that people measure latency and response time that are interesting. But to show you that I've actually done actual hands-on work with garbage collection, here's an actual picture of me doing that. This machine in my kitchen is called a trash compactor. Do you guys have trash compactors here? So the job of a trash compactor for lazy Californians is, it sits where the trash can would normally be, and you put your trash in it, but usually dry trash, not stinky trash. And it compacts the trash down. And it basically does minor garbage collections during the week. So you get this very compact trash bag, and you only have to do the full GC once a week, where you take the thing outside and dump it out, right? And I've had one of these for 20 years. It's very effective, very, very nice. But you can see that there was a bug in my trash compactor. The compaction factor wasn't working right. There are fragments, and they're coming out the back, and they're preventing the allocation of new garbage space, So I had to take it apart, take the fragments out, fix it. And I thought it would be funny to take a picture of that with the actual garbage collection theory book at the same time. But the most important thing about this picture is it was taken in 2004. So I've been thinking this is funny for 12 years. And I really need new pictures, and I'm lazy, I know. But it's a nice picture, and I look better there than I do today. How many of you have seen any of my talks before? Okay, a few. How many of you have seen this picture before? The same number. See, I'm lazy. I use them everywhere. Yeah. Okay. So I have a long history of building things, about 30-some years of working with computers. I'm pretty old now. And that means I've made a lot of mistakes. And some of those mistakes I learned from. And some of what we will talk about today is those learned lessons, things that I know I did wrong, very wrong, when I was looking at these kind of things. And I learned the hard way about them, and then started looking around and noticed that it's not just me. It seems like everybody's doing it wrong. So I started talking about it, became a very popular subject, and I used the same title and the same names for the talk, but I change the slides pretty much every few months, so it's different content all the time. So, you know, I like to basically depress people by telling them about all these wrong things that we do and how bad the world actually is. So at this point, I need to give you guys a choice, a responsible choice. Before we go any further, we have a choice to make. You can take the blue pill, and you can go back outside, and you can keep believing whatever it is you want to believe about the world of latency and response time. But if you stay here and we'll take the red pill, we're going to go down the rabbit hole and see exactly how bad it is, or a little bit of how bad it is. And it will be a little scary, and the world is not nearly as beautiful as you think it is. Most of what I will tell you does not have good answers. It's just bad news. But some of what I will tell you will show you how you might be able to look at things in a more reasoned way and maybe help you think about your systems differently. So let's start looking at the subject itself, latency. And when I say latency, I use latency and response time as interchangeable meanings. It's the time from when something starts until it ends, the time from when I send a request until I get a response, from when a message enters until something leaves, from when I hit this thing until it makes a sound. The latency of action of something. And what's important to understand about latency is it's very easy to measure the latency of one thing. It's a number. But the latency of one thing doesn't give us almost any information. We usually are dealing with many occurrences, and we're trying to talk about how the latency behaves for the many occurrences. We have 1 million operations that happen today. They're all the same thing, but we're trying to say how did the latency behave, not what was the one that happened at exactly here or that one, but for the whole million. And unfortunately, it's very hard for us to think about 1 million numbers, to think about it, to talk to other people about it. So we naturally want to find a way to discuss it, to summarize it, to describe some things about it that are the quality of latency, so we could talk about it, good, bad, high, low, and compare and communicate. When we look at latency, every operation has its own latency. Even if you did exactly the same thing 1 million times, every one of those took a certain amount of time. And it's the behavior of those 1 million numbers that we really are trying to describe. So every one of the operations has its own latency, and we want to describe the behavior. What we actually want, if you ask people, what do you want the latency to be, they say good. I want it to be good. I want it to be fast. And how do you want it to behave? I want it all to be fast. Everybody's exactly the same, and it's really fast. That will never happen to you. That would be a beautiful world if it really was like that. But our job in describing the latency is to explain how not like that this is. Right? It's not fast, or it's not fast all the time, or sometimes it's not fast. So we're trying to talk about how. An example of a simple summary information set about latency is to say the common latency was X. Most of my numbers were around here, or things like that. That's a piece of information. Here's 1 million data points, most of them were around this number. That's useful information. It's a small piece of information. It doesn't tell me a lot about the behavior, but it's one small piece of information I could talk about. The overall picture is a lot more than that. So we'll talk about how people describe latency, what they use to visualize it, to summarize it, to communicate a little bit, and then I'll give you examples of things that help you summarize it and think about it a little better as we go forward. But let's look at a common way we look at latency. This is a chart from one of the most frequently used monitoring visualization tools on Earth today, Grafana. It's an open source tool for looking at time series databases. You're looking at a chart of response time lines over time, over about 2 hours. The actual lines there, because the text is low, the top red line is the 95th percentile. Below that is the 90th percentile. Then the 75 percentile, the median, and the 25 percentile. So each color is a separate percentile of the same response time data. And this is 2 hours. So we have a picture, right? And this will often show up as a dashboard along with 10 other dashboards for your cluster or your data center or whatever that is. So we often look at pictures like this to get a feel for the latency behavior, okay? But when we look at the picture, it's hard to just say, okay, so that's what it looked like. If I was on the phone and I talked to somebody and say, how did latency behave? I can't say, well, it looks like this. Yeah. It's hard to communicate. So I'm probably going to summarize it in some way or talk about interesting things. What looks interesting in this picture? The spike, yeah. I put it there, so you said the spike. I didn't actually put it there, by the way. I took this screenshot from the front page of Grafana. So there's a spike there, and when we look at it, our eyes go straight there, right? Something interesting happened around that time. The 95th percentile spiked up. It went outside of the range that it normally was. And you can see that the 90th percentile spiked up a little bit too. But the other ones didn't. They stayed around the same range. So something happened that affected the 95th percentile, affected the 90th percentile a little bit, but the rest of them weren't. So we probably want to figure out what went on, maybe zoom in there, maybe look at stuff, something probably went wrong. I just went through the exercise of wasting 30 seconds of your life. This chart we're looking at has no useful information for monitoring latency at all. There is zero good information here. This is not a chart for monitoring response time, but unfortunately it is the one most people look at. So let's look at the number one reason why this chart is very, very bad for you. What does this line mean? This is the 95th percentile. What's not on this chart? The bad 5%. This is a chart of the 95% good things that happen. The bad 5% are not here. We threw them away before we've plotted the chart. It's a censored chart. This is what I like to call the feel-good chart, the only show you good things chart. It's a great marketing chart. This is a good chart to show your boss when you are failing but you want a bonus. It's a good chart to show your customer when you have a service level agreement, you're completely failing at doing it, but you try to convince them otherwise. This is a chart of all the good things that happen with all the bad things thrown away. 5% of things are worse than the worst thing on here. It is a censored chart. It is not what you want to use when you want to monitor a system and know when things are wrong. It is the thing that tells you only about things that are good. And when things went bad enough to do that, more than 5% of things were bad. We don't know what happened the rest of the time. So this is a chart for doing that. It's very effective at achieving that. So if this is what you want, that's how to do it. So I'm telling you how to trick your boss into giving you a bonus, right? Unfortunately, this is what our tools naturally do. So well, if you doubt that, because that's just a demo chart from a website, I was giving a talk about this in Australia a while back, and I showed that chart, and one of the other speakers that was in that same tour was in the audience, and he was texting with one of his colleagues and said, it's interesting, what does our chart for response time look like? And they went and they pulled their New Relic data, and they showed this. That yellow line is the 95th percentile. Then the green line is the mean, the average, and then the red line's the median. You see there's differences in behavior. So he said, okay, that's the 95th percentile. Do we have other data? What's the 99th percentile look like? That's what he got. You see where the yellow line is? That's the same yellow line. Okay? So if you're wondering if there are bad things hiding above that, by definition, there are bad things hiding above that, and those bad things are often very big. So if that's what we censored out, right? So, you know, the scale is different, everything here is different. So this is a much, much better chart, right? You see the 99th percentile. What's missing here? The bad 1%. This is still censored. Things are much worse than this. That's the real world. So whenever somebody talks about percentiles and doesn't show you the things above them, you're basically censoring the bad things. You're only looking at the good things. Now, if you actually look at the 100th percentile, the maximum, it tends to look like this. The scales are, again, very different. This is not the same data. This is actually sampled from a Cassandra system. And the reason I believe that we plot percentiles in many colors of them is we like to see pretty charts that have a lot of colors. The problem with this chart is you can only see one color. The maximum lines usually go straight up and then back straight down. So all the other percentiles are inside that spike. You can't see them. So it's not pretty. And unfortunately, the numbers are really depressing too. But this is the one honest thing you could do with your data. Things were that bad. How many we can talk about? But they did get that bad. This happened at that frequency on those events. So, you know, we can't see percentiles inside, so we tend to do other things. Now, the chart that I showed you is, I have this in a blog that I call Latency Tip of the Day. I haven't written in it in a little while, but there's several of these latency tips of the day. And the actual format for the blog is I will tweet a very short latency tip of the day, and then I'll rant about my own tweet in the blog entry. So there's some interesting ones there. This specific one was, what is wrong with this picture? And the answer is, everything is wrong in this picture. Not just the one thing I just talked about, okay? So when you look at the tip, here's a tip to take away from that. If you're not actually showing, reporting, talking about how bad things were, what the worst case was, ask yourself why. Who are you hiding this information from? And why are you hiding it from yourself? And I've heard people talk about, well, I don't need perfection. I'm not saying you need perfection, but it's probably good to know how bad things are. So, you know, that's what you're doing if you are not looking at the maximum. It's okay to look at it and disregard it, but don't censor it. So what else is wrong in this picture? I'm not going to go through all the things, but here's another very common one, a very annoying, very common one. Remember this picture with the, I need to talk on the phone and tell somebody how things behaved. Out of this entire set of information, if somebody asks me, what did the 95th percentile behave like? What am I likely to say? There's only one number on the screen. It's that number. I'm probably going to use that number to say something about the 95th percentile because it's the only number on the screen. Now, what does that mean? What does it mean to talk about the average of the 95th percentile across 2 hours? I mean, seriously, what does that mean? And unfortunately, the answer is, it means absolutely nothing. This is a random number. It has no relation at all to the 95th percentile, except that we know that it's not higher than the highest and not lower than the lowest. But that's all that we know. To give you a specific example to walk through the simple arithmetic of how wrong it is to take a percentile and average it, let's go and average a percentile that's very easy to think about. The 100th percentile, the maximum. So I have some results here. I picked 15 data points. And in each minute, this was the maximum latency I saw. Those are just numbers. In each minute, that's the maximum. So we have 15 minutes. Now, I can do arithmetic on this. I could take these 15 numbers and average them. The average is 42. I carefully picked the numbers. And we could say the average 100th percentile over the last 15 minutes is 42. Do you see 42 anywhere in there? Is 42 anywhere close to the 100th percentile of those 15 minutes? Is it close to where most of them are? It's a random number. Okay. The maximum for the last 15 minutes is 601. It's not 42. And no number happened anywhere near 42. Nothing even close. It has no relation at all to how the percentile behaved. It is simply the arithmetic mean of a bunch of numbers that have no business being averaged out. So if it's wrong to do that for the 100th percentile, it's wrong to do that for any percentile. This is just invalid math, invalid arithmetic. It has no meaning. You could take all the percentiles, scramble them together, decide to take any digits together and make up a number. It'll be about as meaningful. So another simple tip. You cannot average percentiles. That has no meaning. There's no discussion about this. There's no sometimes. There's no, it gives me a good feeling for how it is. Most of the time it's good. No, it isn't. Percentiles cannot be averaged. Once you've summarized the percentile, all you have is that number, and you cannot summarize it with anything else. Unfortunately, that's what all the tools that plot response time do. They will take all the numbers and average them and give you one number for the result. So your job from now on is to ignore that number. Do not look at averages of anything that has to do with response time. It is misleading. It has nothing to do with where most things are, where half the things are. You can't make any statement about the average and the data except that the average is somewhere between the min and the max. Okay, so percentiles. Percentiles are actually very useful ways to talk about information. Unlike an average, it has a meaning that's fairly clear to understand. If I say the 99th percentile, it literally means 99% of things were this or lower, and 1% was higher. Not maybe higher. 1% was higher than this. That's what a percentile means. It's how much is on each side of the percentile. The only percentiles that everything is on one side of are the minimum and the maximum. Everything else slices data. So percentiles matter. They're actually good ways to reason about things when you want to say, what are the chances that something would happen? What are the chances that it'll be better than this? What are the chances that it'll be worse than this? That is a good way to think about what I want, what my requirements are, what I want my system to be. You don't have to have perfect systems for everything. If you're building a heart pacer, you probably want a very reliable system. If you're building a web advertising system, you don't need 99.999% success at putting things in front of the right person at the right time. If you just do 99.5%, maybe it's okay. You know, you make money. Sometimes you don't make money. You don't lose money, you just don't make more money. Right? You can do a lot of things to improve how much money you make by 0.5%. So when we look at numbers, we tend to look at percentiles, 95th, 99, something around there, maybe 3 nines. And often when I look at the 99th percentile, people say, I just want to know that. I don't need to know more. I don't need perfection. And that's okay when we talk about things like user experiences. I'm okay with 1% of my user interactions being worse than something. But you need to be careful when you think about that. Are you okay with 1% of your users having total failure? If that actually happens to you, then after a few days you have no users. Right? If 1 out of every 100 attempts fails, people stop coming. But let's say you have something like I described before. It's, you know, you don't lose anything for not doing it, you just don't make even more money. So your goal is to have a good 99 percentile of experience. But 99 percentile of experience measured from the outside is very different than 99 percentile of a technical operation on a piece of software you guys measure. And the simple reason is, for one interaction with the world, usually there are a lot of little interactions inside of databases, message systems, search engines, caches. So let's look at whether the 99 percentile is a good indicator for behavior outside of a system. So for example, if I looked at the 99 percentile of some internal system, like one of these, a search engine node, a key value pair store, a database system, or content network of some sort. And I measured the 99 percentile, but I didn't look beyond that. What are the chances that in a single web interaction, for example, if I go to a website, click once, that I will see worse than the 99 percentile of one of these things? Let's pick a very simple one. The 99 percentile of HTTP request response time. Very simple thing to measure. That's what a lot of load balancers, load generators will measure. So I have this number. What are the chances that I will experience worse than that if I click now? So a while ago, I went to some websites with my browser, and I put on the debug mode, and I clicked once, and I counted how many HTTP requests were sent back and forth before the web page completed. This was one click. And what you have there is the website name and how many actual resources were fetched as separate HTTP requests. What you can see is there's an interesting number trend here. Most of these are above 100. The shortest one in this list, which is the very clean google.com search page that has nothing on it, was 31 different requests. Okay? Now, if we act very optimistically, imagine that when I clicked, it already knew what 31 things it wants to get and got them all, and they came back. Not that it got one that told it where to get the other that told it. Ignore the serialization effect and simply ask the question, if I went to get this many requests, what are the chances that my page, my experience would take longer than the 99 percentile of one operation? Here's the simple math for that. The chances for experiencing larger than the 99 percentile in one click is above half for everything except that Google Clean page. That Google page, that's only 1/4. 1/4 of all clicks are going to see worse than the 99 percentile. You look at Amazon, 85% of clicks will see worse than the 99 percentile of one HTTP request. So when you look at your request response time, keep in mind that if you're looking at one operation out of a lot, that aggregation of many of them mean that you need more nines if you want to see what the actual experience looks like. So here's the tip that goes with this. Most of your page loads will experience larger than 99 percentile of the individual request response time on a server. That's a sobering thought, because what we usually measure is how the server reacts, not what the total experience is. And the simple rule of thumb is add 2 nines to what you want, assuming you have about 100x operations in the micro level as you have at the macro level. Now, there's a different way to try and slice this. If we needed to pick percentiles, because we can't talk about all the percentiles often, which percentiles are important? Let's look at 2 percentiles here, the 95th percentile and the 99.9 percentile. That seems almost perfect. And the question I'm going to ask with simple arithmetic for this is, if a typical user session had 5 clicks in it, and each click only gathered 40 resources, so almost as clean as the Google page, not a lot of information. And that's all, that's what a session is, very short. How many of my users will not experience something worse than the 95th percentile? Again, I have no information except that that's the 95th percentile, and I'm going to assume on distributions and such. And the simple answer is this. That's how many users see better than that. 99.997% of your users see worse than the 95th percentile. Why did we have it up on that chart? It's something that has no meaning to the vast majority of your users. They're seeing much worse than that. All you know about this line is pretty much everybody sees worse than this. That's the only information. But we tend to look at it. If we ask the same question backwards, of basically how many of the users will experience at least one response longer than this one, then that's 18%. So 82% of users will see better than the 99.9 percentile in this case, this scenario. So of these two, that 99.9 percentile is a lot more representative of the majority of your user population, of the common case, not the rare cases. The point here again is measuring individual things does not tell you what aggregate behavior looks like. And aggregate behavior is very important because that's what people actually experience or external systems experience. Some more examples of gauging. If a typical user session had these 5 pages with 40 resources, we can ask a question of what response time percentile do I need to actually watch if I want to know what my 95th percentile user actually experiences? Because that's a much more proper business question. I want to know what most of my users do, what 95% of my users actually experience. And if you want to know that, you need to look at that percentile. And similarly, if you want to know what the 99th percentile, you want to look at 4.5 nines. And these are not big aggregate numbers. The point I try to make here is that percentiles matter, and percentiles need to have a lot of nines in them for them to have any useful information for aggregate behaviors. Now, if you're able to measure the response time a human sees, for example, from the browser until the page completes, then you can actually measure the 95th, 99, whatever it is you want. But if you're measuring the individual operations on a wire, the individual operations on a server, which unfortunately is usually the only thing we actually have data on, then you need to take this math into account. So again, a short summary. The median response time is the number that 99.99999, a lot of nines, page views will be worse than. And by the way, this is an actual calculation, but for that calculation, I tried to see how many, I did the math on how many repeated things I could do before that overflowed my calculator and show 1.0. And you know how many? 42. It really works. It is a magic number. You know, go to put that equation in, put to your calculator or Excel, and see at 43 it overflows. It shows 1.0. So it's cool. Okay. So why is it that we don't actually have these many nines of response time? Why is it that all these tools show us only 95th, 99, maybe 99.9, when none of that actually represents the bad things that happen? And I believe that that's a combination of 2 things. The first one is you can't average percentiles. That math doesn't work. Hopefully you got that. But the other part is we usually collect this information with systems that collect a lot of data about latency in a certain period of time, but can't keep it. We can't keep all the latencies. So we have to summarize somehow, and usually the summary is, in this 10 seconds, that was the max, that was the min, here's some percentiles. So we have a summary for the 10 seconds, and we throw away the 100,000 good points that we had there in the cluster. And then we do another interval, because we only have summaries of 10-second intervals, or 1 second, or 5 second, or maybe 1 minute. It's not enough operations to get a high number of nines in the percentiles, right? We only have the 99 or 99.9 percentile of the interval. There weren't more operations there. And when we have a lot of intervals that cover a half hour, an hour, or a day, there's no math that could put them back together, which is why our tools tend not to show them. So here's the little piece of good news. A piece of open source software I've been working on for a few years now is called HDR Histogram. It's a data structure and kind of a set of utilities around it that let you capture things like latency information in intervals and log them and keep them in a way that later lets you add them and aggregate them together without losing information. So you can actually look at all the percentiles. You can see the 95th, the 99, you could go all the way to 5 nines, 8 nines, however many nines are in your actual data. And you could go look it up on GitHub. I built the Java version of this and kind of evolved it over time. It's become fairly popular as a data structure for holding latency information. There are multiple language ports. There's a C port, a C# port, a Rust port, a Python port, a Go port. None of these I built. Other people built them. I'm still waiting for somebody to build a JavaScript port. I somehow couldn't convince anybody to do that. I don't want to do it. But you basically, it's a data structure designed to be fast, simple to use. You just put your latency information in it. It's really fast in the sense that on this laptop I can log 200 million latency data points per second into the data structure in one thread, which is faster than I can measure time on this laptop. So if you have measured time, you can afford to put it in this thing. And then you can log it and analyze it later. And there's more and more tools coming that are there. Examples of things that use it, there's some tools I've built like hiccups, and we've gotten the Cassandra people now to put it in the Cassandra stress thing that it reports with. YCSB uses it, a few others. And anybody here familiar with Asterix? The Netflix library that kind of makes things kind of circuit break and not fail and not overload your system. They use HDR histogram to log information about latency. So I'm kind of proud of people are listening. So there is a little bit of good news. There are ways that you can look at latency and analyze it and not lose the many nines and be able to see what it behaves like. So let's look at what happens when we actually look at that data and how it contrasts with what we think data behaves like. The subject I like to talk about here is latency wishful thinking. We all kind of wish that latency behaved a certain way. We learned some statistics early in school or late in school, and it would be really, really nice if the distribution of latency actually had this bell curve that we talk about, because if it did, then we could represent it with, we have 1 million data points, but we could talk about an average, a standard deviation. Maybe if it's not quite, we'll talk about skewness and kurtosis and other shapes that tell us what it looks like. It would be really, really nice if it looked like that. Unfortunately, it doesn't. And the logic we usually apply is to say, if I have a few data points, somebody told me the average, the 99th percentile, the maximum, a few other things, I get a feel for this shape that I don't see. And with a few numbers, I can get a quality. I can describe the behavior of latency and communicate to others, and it's simple over the phone. I get an intuition for it, right? A different way to look at the same logic is to say, I've covered 99% of the spectrum. I don't need perfection. How bad can it really be? And by the way, by definition, worse than everything you just measured, right? You've covered 99% of the spectrum. Everything else is worse than what you've seen. But it's very natural to say, I've seen most of it, and I think it's kind of concentrated there. And that's not how it behaves. So let's look at some real world data. The data I'm going to show you is actually from a trading system. But the y-axis here doesn't matter. You see the same pattern of behavior whether you're looking at microseconds or milliseconds or even seconds. This is a trading system, a good trading system. Engineers have worked on it for quite a while and made it really good, consistent in response time over percentiles. And that line there is, that's 50 microseconds. In and out of a system, really fast. And not only is it really fast, look at how flat it is. That's pretty nice, right? It goes all the way past the 99th percentile, and it's still pretty flat. But what happens if I look a little further to the right, right? What's hiding there? Well, if I scroll to the right, I see this bump. Now you think this bump is bad, right? If I scroll further to the right, I see that bump. See the little bump? That's the previous bump. This is the actual distribution of 1 million data points on a trading system over a period of about an hour. Here's some interesting observations. The ratio between the low point and the high point is 1,000x. 3 orders of magnitude difference between the low and the common to the outliers that we think are maybe not very far away. This is a natural behavior that you see on latency curves if you actually plot them with something like HDR histogram that lets you see this. When you're not just taking 3 numbers and saying, well, down to 3, I think it's probably smooth. You actually plot it, you see these bumps. The bumps represent interesting modes of operation. Let's debunk another interesting thing, and that I've already started telling you not to do, and that's that distribution here matters and that it has some hint about the behavior of data. This is a set of data points like that. I highlighted the pink one there. And here is the mean and the standard deviation computed on these 1 million+ points over an hour. That's just the math. I took all the numbers and averaged them. I took all the numbers and computed the standard deviation from the mean. Those are numbers. It's correct math, it's correct measurement. Trust me, I checked it, okay? But you see the standard deviation is 0.21 millisecond, the mean is about 60 microseconds. But here's another data point. My 99.999 percentile, the 5 nines here, is 38 something milliseconds. Now, that's 184 standard deviations away from the mean. In case you don't remember your basic stats, in a normal distribution, the 5 nines are supposed to fall within about 4.5 standard deviations for the mean. If it's not very standard, maybe 6, maybe 7, maybe 8 standard deviations. That's 184 standard deviations. If this was a normal distribution, that result couldn't happen even if we had 1,000 Big Bang events between now and when it would happen. It will take a very, very long time before that is possible. It's an impossible practical result to have, but here it is every hour. What does this mean? Did we compute something wrong? Did we measure something wrong? No. It simply means that this is not a normal distribution. And because it's not a normal distribution, it means that the average and the standard deviations are completely meaningless numbers to describe this data set. If you use those two numbers to describe the data set, you immediately think bell curve around the mean. There are no results around the mean, and there are results that are 184 standard deviations away from the mean. It doesn't look anything like what you're imagining. So we have some unlearning to do about intuition. And if you want a lesson or take away from what I said so far, how many of you, say in the last 6 months, have seen a response time report that talked about an average response time? Be honest. Okay. How about a standard deviation response time? Okay. So from now on, take a black pen and erase those numbers. That's good for you, but it's even more important for the other people that work with you that haven't been to this talk. Because every time you show that number, you keep that number, that means somebody will read it and think it means something. When I showed you the 95th percentile line and the spike, your eyes went straight there. It must mean something because it's there. It's interesting. If you show a standard deviation number, people read it. You show an average number, people read it. And they tend to believe that it has something to do with the information we're talking about. It's not just not useful, it's misleading. It tells you the wrong thing. So let's talk about some intuition that we probably need to unlearn in this space. If we look at a classic way we think of response time behavior, one of the classic behavior charts is here. This is a 45-year-old chart from an IBM Kick server document that describes how response time behaves as a function of load. So the definition here is there's a good range, there's an acceptable range, and an unacceptable range. At the good range, response time is good. As we increase the load, it gets worse and worse, becoming acceptable, but then crossing into unacceptable at some load. What this represents is the intuition that response time is strongly affected and dominantly affected by load. So it's good until I load things too much, and then it's bad. That's what this shows us. But let's ask some simple questions about this chart. That says response time. Which response time? Now we talk about the average, the maximum, the median, the 99th percentile. Which is it? Depending on the answer to that, that chart will look different. Different percentiles will have a different line here. Usually it's the average response time, which is a meaningless number, right? But that's usually what we mean. But more importantly, we have this basic assumption that if we increase load, latency grows, and therefore load is a dominant factor in latency behavior. But and if any of you have run actual load tests to look at actual response time, you've probably seen these kind of behaviors. So a common way to test systems is to take the system and say, let's load it, see how it behaves, load it more, see how it behaves, load it more until it breaks, or maybe I'll ramp it up for 30 minutes. Most load generators have an automatic function for doing that. Right? So what you're looking at here, and by the way, I just took charts from the web for this. I'm too lazy to do it myself. This light blue line is the load. number of virtual users hitting system. This spiky black line is the response time. Not measured that great, but still, it's the response time. If there's one obvious thing here is the response time does not correlate with the load. We have these things here. Very high response times at low load that are much higher than response time at some higher loads. Those are not caused by the load, at least not directly. Why do I have a much better response time later than I have earlier at a much lower load? Right? By the way, I call these things hiccups. And they're natural. If you actually look at response time over time, you tend to see that. Not if you average it over an hour. Just every interval. The numbers will go up and down. Even the averages will go up and down. So what this basically says is increasing the load is not the reason for spiky response time. Now there is, you can see down here, there is a bit of a correlation. As this grows, the bottom of this line grows. If I did average this out over much longer periods of time, I'll probably see a correlation between them. Because yes, as you grow the load, some queuing happens and things wait in line. But usually these spikes are not that. What are they? Well, we don't know. I really don't know what the system does. It's just an output that I saw in a report for a load generator. But most of the time when I look at systems, that's what they look like. That's what actually the data looks like if you look at it at spine interval resolution. And when you think of what that makes that happen, the easiest thing to say is that's noise. Noise is the name we give something we don't understand. But what I found is that usually when you find the explanation has something to do with not the load, but the amount of work done so far. I call it accumulated debt. Most computer systems, we would like to think computers are continuous, smooth operating things, but they don't work like that. They work in quanta. They do one instruction at a time. You get a little bit of time in the CPU, then somebody else gets time on the CPU. The quanta go across all the levels. You get interrupts, you get context switches, you get operating system quantums, you get garbage collection pauses, sometimes you re-index a database, sometimes you flush your disk. Every one of those things is not a result of the operation you just did. It's a result of all the operations you did so far that you didn't pay for. And now it's time to pay. I had the CPU for 10 milliseconds. It was really fast. But now it's your turn. So I don't get to do anything. I'm paying for all the operations, not this one. Usually that results in a spike. At different levels, different magnitudes. I just gave you examples of the things that could make them happen. But that spike is usually the system paying for something it didn't do but needs to have done an aggregated piece of work on. And this happens at all levels of software and hardware in computers. Hypervisors do this, operating system, context switches do this, I/O systems do this, JVMs do this, garbage collectors do this, databases do this, disks do this. Everybody does this. And each one of those has a different level of quanta. And I have no idea what this system did, but it looks natural. So these hiccups, you can start looking at them and say, what do they actually typically behave like? And I look at hundreds of these charts. Part of my job is to look at people's response time to say, well, see, now we can see how we do good things for you, and I can compare before and after pictures. So I look at a lot of them, and they tend to look like this. Hiccups are strongly multimodal. They're not these smooth bell curvy things. It's not, there's no averages to them. They actually tend to be something that behaves like this. There's a common mode, a good mode. This is the mode we would like to believe everything is. And then there's some sort of a bad mode. And then there's a worse mode. And depending on your system, there might be a lot more of these modes. But the system is not smoothly working between them. It's shifting from being good to being bad to being really bad and back. And usually it's a desert between them. There's nothing there. It's doing this or that or that. And around each one of these, there's a little bit of noise. Each one of these is a separate data set in a way, and a separate mode of working in the system. It was really fast, except that sometimes it had to miss in the cache, and it's really slow. Those kind of things, right? And what do we do to deal with hiccups? Well, we do that thing with the charts and don't tell me about the hiccups, tell me about the good things. I don't want to see those. I don't know what to do with them, right? So let me give you instructions on how to do that. You take a shovel and you dig a hole. And then you compute the standard deviation and the shape of the curve of the hole. Not exactly, but this is I'll tell you a true story that happened to me more than once. It's a shame that it does. It's kind of part of what made me make these talks happen. When I talk to people about our product, which makes response time behavior better, that's its purpose in life, I usually like to ask them questions about what they know about their system already, because I don't know what they measure, and I probably think they measure wrong, but I don't want to offend them before I have data. So I'll ask them to describe what they know about the system. And they'll say things like, my average is this, and my maximum is this, and I know these percentiles and the rates. And I'll wait for them to finish, and I will ask them a question that they haven't already answered. So if they said, I know what the 95th percentile is, I'll ask, do you know what the 99th percentile is? I'll pick a number they didn't say, and I'll ask them about that number. And the reason I do this is I want to figure out where they go and get that number from. The reason for that is usually if they can get me the percentile that they haven't already said, that means they have the data somewhere that they can go and look up the data from, which is good news, because that means there's a lot of data and I can ask for that data, and I want to analyze it. So I started doing this early on, and I found this very interesting pattern. A lot of the people that I would ask this question on, it would go something like this. I would say, what do you know? And they'd say 95th percentile max, and I'd say, what's the 99th percentile? Say, hold on, I don't have it, but give me a couple minutes and I'll get it for you. They'll go off, come back, and they'll say, the 99th percentile is this. I'll say, so great, can I have the data that you used to compute the 99th percentile from? Because you probably have all the data, because you could compute 99th percentile. And they say, no, we don't have the data. So I'll say, well, how'd you come up with the number? Here's the answer. They had the average. They had the standard deviation. They know that the 99.7 percentile is 3 standard deviations away from the mean. So they computed where that would be, and that must be where the 99th percentile is, right? This literally happens to about 1 in 10 people when you ask them the question. What we just went through is we had 1 million good data points, but it's hard to talk about them, so we took 2 data points, average and standard deviation. We threw away the 1 million data points. Then when somebody asked us what's the 99% of the 1 million data points, we said, I really wish that it behaved like this. So under that wishful thinking assumption, what would it be? And that's how we answer. This happens way too often. Erase the standard deviation and the mean from every report you have from this day on. You want a number that describes most or the common? Use the median. Use the 90th percentile. Use a percentile. They mean something. These don't mean anything. And I apologize for all the statisticians here. Statistics in the normal distribution, Gaussian kind of range of math, and latency behavior do not belong in the same universe. Okay? It's only in fairy tales that they work together. So this is always, always wrong. Now, what you could do, as I said, HDR histogram is actually a useful way to look at things, and you can plot all the percentiles. And if you plot and visualize all the percentiles, you get very useful information that is easy to see. So this is, again, maybe stuff you can learn from. What I'm looking here is a multimodal system. It has 3 modes. That's the good mode, that's 1 bad mode, that's the 3rd mode. Only 3 modes. And by the way, it's very common to see a handful of modes in a system. They're that simple, that smooth. This is a real telco system. It's not made up data. That's the percentile curve. For any percentile, I have a value. And that yellow line is the requirements line. I can plot a requirements line and say, if somebody said that I have to have the 99.5 percentile better than this and a max better than that, I can see visually if I fail or pass that requirement. If the numbers are all below the line, great. If something crosses the line, that's a failure. Here's a very interesting effect of looking at this picture. Imagine that you have a system you worked on, you're really proud of it, and you send it off to acceptance testing with the telco system, and they test it against the requirements and it failed. And you don't look at this picture. They say, look guys, I mean, it handled the load, but it failed at this percentile or something. What's the most common thing that you think engineers will do when the system comes back and they say, make it better? How do we make a system better? How do we make it carry more load or perform better? Right? It failed performance tests. What we will commonly do is say, okay, let's break out our tools. Let's profile this thing, see where I'm spending too much time in code. Maybe I could optimize the code. Maybe I could shorten some paths. We can make this better. We're good engineers. We can make it better. And then you spend the next 3 weeks making it better by taking this number and making it lower. Because guess what a profiler tells you? It tells you where your average is. It tells you what affects your average. It tells you what the common case is. A profiler does not tell you how to make outliers better. It tells you how to make the average better. When you spend your time to improve your loops, to make them faster, you're not doing anything good about that outlier. In fact, a lot of times that's how you get that outlier. Think about what the job of optimization is. What do you do when you optimize? What does a compiler do when it looks at code and says, this is very rare. This happens 1,000 times, this happened once. So if I make this twice as slow but make this 1% better, I win. On the average, I got better. If I reduce the common case and raise the outlier, the average got better. That's how these things happen. Not only how they happen. But when you go and try and make the system better, you're most likely shaping it the opposite direction. Looking at the picture this way highlights the fact that our failure happens at a high percentile. Our job is to find out what makes the rare bad thing happen and try to eliminate that. And often that would happen by improving the outlier and making the common case worse. It doesn't have to be. Maybe you just found some noise you can eliminate. But if I could drop this below that line and increase this by 2x, I can go home. My common case is 10 times better than it has to be. I fail in a different place. That simple visual can save you weeks of work on the wrong thing. So try to keep it in mind when you're thinking of response time requirements and whether or not you're looking at the right problem. Unfortunately, understanding and figuring out what makes outliers happen is black magic. Not a lot of tools are useful for doing that. Most of our tools focus on the common case, focus on throughput or average performance or where I spend most of my energy, and that's not most of anything. That's 0.01% of stuff, which is exactly what profilers and samplers don't know about. But start using your mind to think of tools to figure those out. You look for events, you look for correlations between events, you look at things and say, what could have done that? And often you'll start finding things. Okay, so, good. So I spent some time depressing you about how statistics that you learned don't apply at all to response time and how the behavior of response time is not what you wished it was. And unfortunately, all the tools you look at are probably lying to you and showing you bad things. But that's not the really bad news. Okay, that was just the beginning, unfortunately. Anybody have a oh shit moment so far, by the way? Okay, good. See, we're in the right place. Good. Okay, here's a bad news piece, right? There's this problem that I named it the coordinated omission problem. It's a simple term, coordinated omission. Omission means dropping things, and coordinated means, well, dropping things in a coordinated way. It's okay to drop data. It's okay to sample, as long as you do it randomly without coordinating with the data. But selectively dropping some data you don't like is not a good thing for figuring out what the data looks like. And the coordinated omission problem is a natural effect in how we measure and display data that tends to omit the data we actually want to look at. I call this an accidental conspiracy because I ran into it and I thought, this is weird. I wonder I don't think this happens a lot, but how did it happen here? And I started looking for it, and everywhere I look, there it is. It's everywhere. It's in our load generator tools, and it's on monitoring tools. It's in our charting tools. All our tools do this to us. And have you noticed how I spell percentile so far? I carefully spelled percentile in all the charts so far. Coordinate omission is what makes the lie in the percentiles I was showing you so far. Right? They're lying to you. That's not the actual data. It's not the real percentile. So let me, instead of just talking in theory, let me give you a couple of examples of how you get coordinate omission and then what its impact could be. The first and simple one is we load the system up with a load generator. We measure, we send requests, we measure response times. We take all the data, we put it in a bucket, and we do percentiles and analysis on it. And let's assume we actually look at all the percentiles and all the data, right? What could go wrong? Well, this technique, which most load generators use, works as long as every request you send responds in less time than it takes until you were supposed to send the next request. So if you are supposed to send 100 requests a second, then if all the requests come in less than 10 milliseconds, you have good, perfect data. But imagine that it takes 20 milliseconds to get a response. Most load generators will wait for the response before they can send the next request. In fact, most protocols cannot do the next request because the next request is something that comes from the previous response, like an HTTP GET. You know, give me the page. Oh, that's what I should get next. You can't take the next step. So you're fundamentally delayed in your operation. So you're supposed to send the next sample in 10 milliseconds, but it took 20, 30 milliseconds, so you wait. And you don't measure. What did you not measure? The bad behavior of the system. You're coordinating with the system. You're not measuring when it's bad. You're measuring when it's good. Another common way to achieve the same thing is not by load generating, but by measuring and monitoring from within a system. I apologize, this is fairly small text for the distance you guys are looking at, but this is a very common measurement technique for latency or response time inside a machine. We're about to do a read operation. We measure the time before, the timestamp. We do the operation, we get the timestamp after. We subtract the two timestamp. This is how long this took. We take that data, we put it in a bucket, and we'll do statistics on it later. Good statistics, correct statistics. What can go wrong here? Well, imagine this operation took a really long time. It's normally a millisecond, but now it took a second. The disk head had an error, it had to retry. The thing I was asking crashed, I had to go somewhere else. Garbage collection paused, I had I/O things, whatever it is. An outlier happened. Rarely, but it happened. So an operation took a second instead of a millisecond. And imagine that I'm doing 10,000 operations a second. By the way, this code is Cassandra measuring its own read response time and reporting the percentiles on it. That's what this code is. It's straight out of Cassandra source code. So in Cassandra, we'll do tens of thousands of operations per second, and sometimes it will stall for a second. So during that second, 10,000 things would have happened, but they didn't. So I have one bad result, followed by 10,000 really good results. Not 10,000 bad results that showed that they've been waiting for that one thing to run. So that's one problem. Right? A large operation delays the measurement start time. The other things are not even in the time window, right? But the even worse thing is we usually measure more than one thing. This is the read latency in Cassandra. But there's also the write latency in Cassandra. And sometimes Cassandra as a database is used as a write mostly database, maybe 95% write, 5% read. My chances of actually being in this window for the read latency when a stall happens is 5%. 95% of reads, 95% of stalls will happen when I'm not doing one of these things. So I won't even have that one bad piece of data that hints that something weird happened. Both of these are examples of coordinate omission. The fact that the system stalled made us not measure what happened when it stalled. So okay, this will noise up our data, right? It'll create some bad data, make us forget some bad things, but how bad could this really be? So let's look at how bad it could really be with some hypothetical behaviors. I'm going to describe a perfect hypothetical system, and then we'll go and measure it. So this system is asked to do 100 things a second. in one client thread, okay, one message system or something. And if you want to do a lot more operations per second, and when you a lot of client threads, do 100 client threads doing this. But from the point of view of one thing, we're doing 100 things a second. And it's a perfect system. Every request responds in exactly 1 millisecond, all the time. It's perfect. It's got plenty of room, it's idle most of the time, everything's good. And I'll take this perfect system, and after letting it run for 100 seconds, I'm going to pause it. I'm going to stall it. I'm going to hit Control-Z on the keyboard and wait 100 seconds. It cannot do anything. After 100 seconds, I'll let it run again, and we can repeat this. 100 seconds it's working, 100 seconds it's not. This is a simple hypothetical definition of what the system behaves like. Now, before we start measuring this, let's talk about what good ways to describe the system would be, what honest numbers would look like. What can we say about the system if it behaved like this? Well, in the first 100 seconds, we know that the average response time, as bad as an indication it is, the average response time would be 1 millisecond, right? That's simple. It's always 1 millisecond. In the other half, the average response time is 50 seconds. Why is it 50 seconds? Because it stopped for 100 seconds, and depending on when I come in to measure, I'll get any number between 0 and 100. If I come at the beginning, it'll take 100 seconds. If I come at the end, it'll be close to 0. On the average, if I just go, how long is it? It'll be 50 seconds during the second half. The overall average for 200 seconds is going to be 25 seconds. There are no tricks here. This is the actual number. I'm not trying to trick you here, okay? We can also talk about percentiles. The 50th percentile is really good. Half the things are really good, but then things go really bad. The 75th percentile is halfway to terrible, or it's already terrible. And the 99.99 percentile is clearly very close to 100 milliseconds. We don't need to be precise here. This is what the system did, and if it did that, this is what you would want your monitoring system to tell you happened. This is honesty. If it doesn't tell you this, it's not telling you what happened. So let's take this system and measure it with a load generator or with a monitoring system to do the things I just showed you before. How many of you have used JMeter to load generate? Oh shit. Okay. So let's measure JMeter. Well, what will we have in the statistics bucket that go into what we get as output? On the left side, we're going to have 10,000 operations that took 1 millisecond each. This is easy to understand. It's perfect. It's always 1 millisecond. In 100 seconds, we did that many. Then the system stalled. So we have this one really, really bad result. This is all the data. This is it. We don't have other data. So we put all this data in a bucket and we do math on it. The average of this is 10.9 milliseconds. It's a little less than the 25 seconds they know it is. But even more interestingly, the percentiles are really good. JMeter will tell you that the 99.99 percentile of this system that was completely off for half the time is 1 millisecond. Because 10,000 out of 10,001 operations took 1 millisecond. That's just the data. This is literally what JMeter reports. When you look at a percentile graph out of JMeter, this is where it comes from. Now what happened here? Why is it lying so badly? Well, if we measure 10,000 operations in some 100-second period of time, we better measure 10,000 operations in any 100-second period of time. We were supposed to measure 10,000 operations when the system was stalled. What happened is we erased a bunch of the data simply because we didn't like it. Well, really because it was hard to measure. So because the system stalled and the load balancer coordinated and backed off, or the monitoring system wasn't able to measure, we just don't have that data. The data we omit is always the bad data. We are looking at the averages and the percentiles of the good data. This is the 99.99 percentile of the happy data. We threw away the bad data. We don't have it. And unfortunately, this happens quite a bit. Now, when I ran into this for the first time, it's not this part that I noticed. I kind of figured it out, but it was something else that hurt us. We wasted multiple man-months of our engineer time trying to optimize a system based on data like this. So let me debunk this myth. I often explain this to people and they say, okay, I understand the averages are no good, the standard deviations are no good, I need to look at the shapes differently, and my tools don't give me any real data. But my job is to make the system better. I don't know what the number means, but I can make it better. So better is better, worse is worse. Let's make you understand how wrong that is. This is how we spent multiple man-months and it made me angry, so I started talking about it. Let's take this system that froze for half the time and take some brilliant engineers and make it better. We know how to make it better, let's not freeze. Unfortunately, we do have to be slower because something weird is going on, so instead of freezing for 100 seconds, we'll answer every question, but in 5 milliseconds instead of 1. So we spent 3 weeks, we improved the system, we go, now go measure it. What will the results show? Well, we'll have 10,000 operations at 1 millisecond and 10,000 operations at 5 milliseconds. Now we're measuring all the data, right? What do the stats on that say? Well, they say that the 99.99 percentile got 5 times worse. I probably did the wrong thing for the last 3 weeks. Let's go back to that other system. It was much better. Making the system better can make it look worse. Making the system worse will often make it look better. The numbers aren't just wrong and off in magnitude, they point in opposite directions, or we don't know which direction. It's not always that this is true, but we just don't know. So you cannot rely on making these numbers better meaning anything. If you're throwing away bad data, it doesn't matter what you're looking at. One more interesting way people try to fix things is to say, okay, I understand. I got rid of all that data. I'm 10,000 requests behind. I can't not ask the questions. So when I wake up, I have to catch up. I have 1 request, I need to do 9,990 requests again. This is what I call cheating twice. So what we did is we erased 10,000 bad results, but we felt guilty for that because there's 10,000 missing results. So we added 10,000 perfect results to replace them. That makes all the numbers look even better. Right? Okay, good. Yeah. Anybody here run constant load generator things like JMeter, like, well, pretty much anything that says I need to run at this rate? The way they react to not being able to run is they catch up, and that's how they do it. They'll measure when they can. When they can is good. Yep. So this is very unfortunate. There are ways to fix it, and I won't get into them right here. But let's turn into maybe some good technique and maybe good news. I don't know if they're good news, but at least what can we do and how can we look at data and compare it? So I'll pop out of the percentiles and
What's making a break?
Let's do one in about 3 minutes, 3 or 4 minutes, okay? So let's raise this and talk about what response time means and talk about it. I don't want to get very academic, but in queuing theory terms. When you look at it at response time from a queuing theory point of view, you actually break down things into the response time, the time it takes to actually get a response, the wait time, which is how long you waited for things, and the service time, which is how long it took to do the thing. And a way to understand these without getting into too much definition is to look at a coffee shop. So here's the guy making the coffee, and the service time is the time it takes the person to take your order, take your money, go make the coffee and get you the coffee. That's service time. It takes them, I don't know, 30 seconds, a minute, that's how long it takes, period. It doesn't matter how many people are in the line, that's how long it takes. But the response time is how long it takes to get coffee here. It's not the service time, is I show up and I have to wait for all these. And if that person takes a 5-minute break and then comes back and makes more coffee, and we measure the service times, we will have a service time of half a minute, oh, 5 minutes, now half a minute. You know, the service time had a spike in it, one spike, and it's correct. He didn't make other coffee, so it only happened once. But when he went away for 5 minutes, the line grew longer. Everybody in the line experiences that 5 minutes over and over again until it draws down. So service time is how long it takes to do the work. Response time is how long it takes the person getting the result to see the result. The only thing that matters is response time. The only thing that's observable from the outside world is response time. But when you measure things inside the system, you usually pick up response time, service time. So that measurement that I showed you from Cassandra, that's Cassandra measuring its service time, not its latency, not its response time. How long it took me to do the operation, when I did the operation. And it is correct to say it took a second and then it took really fast. It doesn't take into account the fact that the line was a second long. Right? What coordinate emission does to you is it makes you think that something that is actually service time represents response time. And that lie completely shifts your perception. I'm going to run through a few comparisons of service time and response time, and then we take that break. So here is, I like to measure Cassandra because we actually built a good tool for doing that. So here's Cassandra in one of these lines. The red line is the service time, the blue line is the response time. They're very close together. This is Cassandra running at 2,000 operations a second. This node can do 90,000 operations a second, so it's almost idle. Why are they so close and so good together? Because this is the effect is going into an empty coffee shop. There is nobody in line. This guy can make a coffee in a second, and I just came in. I always get the front of the line, everything is good. They're very tight. But as we increase the load, we do have a higher and higher chance of being there, some long operation took, and now we have to wait behind it. And that doesn't happen at saturation, it happens well below that. So if I increase the load to about a quarter of what the system can do, start seeing the separation. That x-axis is percentiles. You're looking at an order of magnitude difference in likelihood of occurrence. If I increase it a little further to about 3/4 of the load that it can actually carry, we're looking at 2 to 3 orders of magnitude of difference between response time and service time. And if I go and come close to saturation, still not saturated, it starts separating and looking like this. The red line is the response time, the blue line is the service time. If I go a little further, and if I push the system to do more than it can, this system could actually do 87,000 operations a second. So let's make it do 90. A very interesting thing happens. They completely separate, they happen at different orders of magnitude, and the reason for that is really simple. The longer this test runs, the longer the response time is. The line keeps getting longer and longer because the system isn't keeping up. The longer I run, the longer the line is. If I double the length of the run, that line will grow by 2x. When real people actually realize this, they often react like this. This is from a Twitter thread on, I put out a tool that let you actually see the red line and the blue line, WRK2, and Kelly Summers, who does a lot of tweeting about performance, tweeted this thing. She likes to use the F word a lot. But this is where I got the red pill and blue pill idea from. That wasn't mine, Once you see that red line, you can't go back. I'll quickly play this. Remember, we had response time and service time, and we were looking at how those compare when we pressure a system. And again, this is what things look like when they're idle. This is what we tend to think they look like all the time. Meaning service time somehow tells us how long things took to get, but it doesn't, except for when you have no line. As you load the system even a little bit, they separate and separate wider and separate wider and separate even wider. A different way to plot this, and one of the reasons I'm showing you the charts now is to show you ways I visualize response time and latency data so I can get a good feel for what it means, okay? So This is a chart format I like to use. It's actually from a tool we call Histogram Log Analyzer that actually we just pushed the source code for on GitHub today. We'll have, if you could get a tarball for it if you want. It reads a histogram log generated by any of the HDR histogram libraries for all the languages and can plot in that log the timeline, what the maximum value is on a timeline, which gives you kind of an intuit, oh, something weird happened here in time. And for the window you're looking at, it shows you the percentile distribution within that window. So over that period of time, that's how percentiles behaved. Now, there are a couple of interesting things here. This is the same data that I was showing before, just the percentile charts. But I'm measuring the service time across the saturation point. This system saturates at 87,000 per second. The left side is the 90,000 per second, and the right side is the 80,000 per second. This is how service time behaves across them. And what it's really showing you is it looks the same. It doesn't take longer to make a cup of coffee when a lot of people wait in line. It takes the same time. And when we take a longer cup of coffee, it takes a longer time to get the cup of coffee because I need to clean the machine. It takes a longer amount of time, but not because people are waiting in line. So it's very similar behavior on the two sides of saturation. The system is keeping up and completely collapsed, but service time looks the same. Service time does not show you when the system collapsed. It doesn't show you how much it can do. There's another interesting thing to look at here that I usually point out. You see the shape of the percentile curve down there? So far, most of the things I've shown you have this smooth transitions and shapes. That's because they're measuring the correct thing. Whenever you have a vertical rise in a percentile chart, you should suspect coordinated omission. Actual response times do not jump from one value to another. They don't go from 1 millisecond to 1,000 milliseconds with nothing in between. Service time does, but when your service time goes to 1,000 people will see 1,000 and 999. You'll see all the values in the middle. If you're randomly and uncoordinatedly coming to wait in line, you will see the entire range and that will actually look smooth. That's what that smooth looks like. So what you're looking at here is not the service time, but the response time for the certain data points. The left is 90,000. The system is not keeping up, and the right is 80,000. By the way, the y-axis here is not the same scale. What we're seeing here is at 80,000 per second, the system is still keeping up. Yeah, the response times spike up and down, but they come back. There's some level to them around with spikiness, and there's a distribution of percentiles. But once I go past saturation, very interesting shapes happen to response time over time. They no longer go like this with some level, they just get worse and worse and worse the longer I run. That's because the line gets longer and longer and longer. If the x-axis was longer, that value would go even higher. And this is very intuitive. I'm sending 90,000 operations per second into a system that can only do 87,000. Every second that goes by, the line gets 3,000 requests longer. It does not get shorter ever. If your load generator doesn't show this shape when you're pressing as hard as you can, it's not pressing as hard as you can. If it's telling you that it's doing 90,000 operations per second, but it's actually only doing 87,000, and the shape is not that, you have a bad load generator. It's a very simple way to calibrate things. So talking about that for a second, this is normalized for y-axis scale, and very different scales. I was just showing you a zoom down there so you could see that, yeah, there's a level. I highly recommend that when you go back to your stuff and next time you look at output from any kind of tool, you calibrate that tool first. So this is an example of calibration. I know that if I ask a system to do more work than it can do, I should get a response time that grows over time. If that's not what happens, that's not what I did, right? If that's not the output I see, I have a bad tool. Another very simple way to calibrate your tools is to do that hypothetical experiment I showed you before. Take your system, load it up, not a lot, and then hit Control Z, count 10 seconds, let it run in the foreground again. You know what happened. You know the system did absolutely nothing for 10 seconds. You know what percent of time that was, 10 seconds in a minute or 10 seconds in 100 seconds. Some amount of time it didn't do anything. You know what the percentiles have to be, at least this bad. Look at the output of your tool, of your monitoring system, of your load generator, and if they don't tell you what you know happened, throw all the data away and don't look at it again. It is useless data. We talked about JMeter before. JMeter is a very good load generator. It is very good at generating load. It is terrible at measuring response time. It's a smart load generator. You can write scripts in it. You could give it scenarios. There's nothing wrong with how it generates load. Don't look at the data that comes from the response time. If you want to use load generators like that and use them well, use it to generate load. Use something else to measure response time. Something that does it correctly, something that passes the simple calibration test. I call it the Control Z test. It's very easy to Control Z, this is bad data, I just saved myself 3 weeks of hard work thrown down the toilet. Every time you do this, you save yourself a lot of work, so start doing it. Unfortunately, what you then have is you realize that you have no tools. But that's better than using bad tools. Wrong tools, right? Okay, so back to this. This is a way to visualize things. I like to visualize a timeline over a percentile chart. I used to call that a hiccup chart because a tool I built called JHiccup, which you can add to any JVM and will give you that behavior for the JVM's own response time, not for your code, for the JVM. So the JVM stalled. The 99 percentile of doing anything on this JVM took 20 milliseconds because I can measure that it stalled for that long, so nothing could have been better. And it's a tool that you can, it's again open source, you can download it, run it using your application, plot this output. It doesn't tell you what your response time is, it tells you the best it could possibly be. So what it tells you is it must be worse than what I'm just showing you. It's a good sanity check though. Okay, I'm going to go through some comparisons and behaviors on latency and response time across systems. And it is important to understand that even though I told you, look, the intuition on load causing latency is not directly true. Latency has its own reasons for noise regardless of the load. It is true that as you load up a system, queuing starts happening, wait lines get longer, and things will get worse. And latency doesn't live in this perfect vacuum where load means I do this much per second. This is a chart that I'm very happy to have from LMAX. LMAX runs a foreign exchange system in London and in a few other places. And what this plot actually shows you is the arrival rate of requests into their system averaged over all the seconds in a day, but showing when in the second things happen. So what you're seeing is in the left, that's the first millisecond of every second averaged. On the right, it's the last millisecond, and there's 1,000 points here. It's a very interesting view because it shows you that even though that red line is the average arrival rate, if you were designed to be able to handle the average arrival rate, you would have queuing and failure happen tens of times every second. For a system that needs to respond in milliseconds, measuring average arrival rate around a second and designing for that is just wrong. You have spikes of arrivals. You have to be able to handle that spike times a bunch if you're not going to queue up. By the way, the interesting thing about these patterns is, can you see there are exactly 4 of these big spikes? And they seem to be at equal distances. This is a trading system. You know what these spikes are? That's Reuters. People trade on information. Reuters takes new information every 250 milliseconds, then people trade on it. So after Reuters ticks, people trade. After Reuters ticks, people trade. That's a natural behavior. There's a clock in the world and robots react to it. Luckily, when we talk about web systems that deal with people, we don't have very good synchronized clocks. So people don't behave like that. People smear much better. But if you look at wider ranges of time, when you say I have this many people per hour. Well, that's great, but what about the 5 minutes of peak when everybody just came back from lunch and logged in? Or when people bet on a game right before the end of the game. The peaks that people hoard together for other reasons, and they're natural peaks that are way above any average you can look at. So when you look at periods of time for how fast am I going, we have this tendency to think of operations per second. Operations per second matter only if you care about response times that are multiple milliseconds long. Sorry, multiple seconds long. If you're looking at response times that are 50 milliseconds, you should think of operations per 50 milliseconds, not operations per second. Is that making sense to people? If you care about an operation that's 1 millisecond, you better look at operations per 1 millisecond, not operations per second divided by 1,000. That's averaging. Okay, so remember this load relationship? I said, hey, the intuition isn't quite right, but there is actually something to talk about here. And in a common practice we need to use this intuition for is things like capacity planning. You can't run all of Google or Yandex on this one laptop. There are too many people that want answers at the same time. The role of capacity planning is to say how many computers do I need to handle the load so people don't become unhappy. This chart tells us when people become unhappy. That's unacceptable behavior. That's the definition of unhappy. And if we look at the system, we can say, how much can it handle? The interesting thing is, the answer to how much can it handle depends on what the service level you expect is. So if you don't say what the service level is, and somebody wants to say, look, I can handle this much, they'll say, look, I can handle this much. I can handle this much doing unacceptable work. Okay? But if you want to ask, when do people complain? When do they say it doesn't work right? Well, that's why they say it doesn't work right. And if you want to ask the system administrators and the DevOps people, how many machines do you need? They say, I need to be here, far away from the bad things. I need padding, I need headroom, I need to be in a nice linear reactive thing where things still grow like this and not like that. I don't want to be anywhere near the collapse point and need. So the answer to how much do you need varies depending on all kinds of questions. But there is a very important point right here, right at the point when things go from acceptable to unacceptable. That point is the sustainable load that the system can handle. It's not the throughput that you can handle in a system without caring if things complete, or without caring if 1 + 1 is still 2 and not 3. It's the system, it's the load this system can handle while it still works within requirements, within acceptable behaviors for whatever percentiles we're looking at. I define that as the sustainable throughput level, and the role of figuring out capacity of systems is to establish what the sustainable throughput level of systems are so we can figure out how many we need to sustain the workload. So here's the definition. Sustainable throughput, that's the throughput you can achieve while safely maintaining service levels and functionality and everything else. It's not interesting to know how fast you can go when you're broken. It's only interesting to know how fast you can go without breaking. So to give you a picture for that, this is not sustainable speed. I can take a red car and I can say, wow, this is cool. And I could press the gas to see how fast it'll go. And when that happens, that was interesting that that happened at that speed. But that's not sustainable. Unfortunately, I see a lot of experiments that go something like this. Nice red car. Let's take it for a drive. Press as hard as I can. Oops, that happened. That was unfortunate. Let's get out, look at the car and say, I don't like the shape of the bumper when this happened. Let's do this again, and if I can see if I can shape the bumper a little different. And do it again and again and again. And we're not doing our job if we're trying to make the bumper look different when we hit the red car into the pole. It's also expensive. Obviously, what you should be figuring out is how fast can I drive the car without this happening, rather than how do I make things look better after this happened. In software, we do this a lot. Zing, our flagship product, is a really cool JVM. Guess what people want to do the first time we give it to them? They want to take it for a drive. How do you take it for a drive? Well, you load it up and you tell it go as fast as you can. And what do you measure? Response time. It will look like that. When you saturate a system, response time sucks. If it doesn't, you haven't saturated the system. So if you measure response time at saturation, there is no useful data except that it's terrible. And it doesn't matter how terrible it is, it's saturated and you shouldn't be there. People don't run response time sensitive operations or systems at saturation because that happens. What we want people to do is to take it for a drive at a certain speed and see if it works, and then at a different speed and see if it works. Do that. It's cheap to do this with software. Press as hard as you can, see how fast it doesn't work. But the purpose of doing that is not to find out what the response time is, it's to find out how fast you shouldn't go. Don't go this fast. Don't saturate the system. I need a system that has room to be in the good range rather than there. And then you repeat and see what you can improve in the system so you could go faster and faster without hitting the pole, without an accident. And the role of Zing is to let you run the same workload at a faster rate before this happens. So let's look at some comparison and how I like to compare two systems or multiple results against requirements so we can establish what works and what doesn't. This is a simple pictorial. If we had 6 data sets and a set of requirements, some of these pass, some of these fail. If you cross the lines, you failed. It doesn't matter how much and where. So these are good, these are bad. If I look at comparing these, and I'm going to go through a systemic comparison of system A and system B running the same workload on the same physical systems with the same data, where you change configuration and you're trying to say, what can I say about this? I improved the system in some way. What does that mean? So here's that system. And this is actually the Cassandra system I talked about before. And remember, I'm not improving the throughput of the system. Both system A and system B collapse around 87,000 operations a second. This is not about running faster, period, right? And here I can compare the response time behavior at 90,000 operations a second and 85,000, the two sides of collapsing points. This is system A and system B at 90,000. Here they are at 85. Dramatic difference between what happens at 85 and here. Now I could go in here and say, wow, look, this blue line, it's twice as good as the red line everywhere. Isn't that great? Well, no, it isn't. That's the red line hitting the pole. Both of them hit the pole. This is terrible response time. And one of the terrible is twice as terrible as the other. Who cares? The only useful information here is don't do that. Do that. Right? That's what we learned from this. You crashed into the pole. Don't look at the shapes. Just don't crash into the pole. So over here we see that there's a dramatic difference if we go a tiny bit slower. So go slower. Now we can zoom into just that part and look at the two systems, the colors reversed here, and say, oh, okay, that's interesting. Across the whole spectrum, short of saturation, this system is better everywhere, almost, right? Good. But that's still not really interesting. Do you want to run at 85,000 a second when you know you're saturated at 87? Is that what you're going to ask when your boss says, how many systems do you need? Are you going to ask for just enough systems to do this? What if you're 2% off? The other thing's going to happen, right? You don't want to be anywhere near here. So the right place to look at the system and compare its behavior is far away from the bad things. So let's go far away. Let's go to half. So at 40,000 operations a second in a system that saturates at more than twice that, we can now look at the separation in the behavior of the two systems. We did something to one of them and it got better. We worked on it for 2 weeks. Now we're proud of it. We want to show our boss what we did. This is how you do that. This is an honest way to do it. It's not hiding information. What do we see here? All the way up to the 90-some percentile, they behave exactly the same. But above that, one of them starts collapsing much earlier. Great. So we could say, hey, the response time behavior is better for the red line here. What can I do with that? Well, okay, maybe I wanted response time that's better, that's nice. But I could do some other very interesting things. I could say, well, what if I had a response time requirement? What if I said, I'd like the 99 percentile to be below 5 milliseconds? This is a database system after all, and I'm going to have 100 of those requests for one thing. You know, it normally answers in under a millisecond. I want the 99 percentile to be below 5 milliseconds. If I asked for that, the red line was already meeting that at 40,000 a second. The blue line here wasn't. It was failing. But what can I do to make it meet it? I can slow the load down until it's okay. There's always an okay load. At one operation an hour, it's probably going to be good, right? Percentiles are going to be great, yeah. So here's the system slowed down so both of them meet the requirement at 99 percentile. And with this comparison, I could say not just this red system improved response time, it improved the carrying capacity of the system. I could say if I needed to keep the 99 percentile below 5 milliseconds in the system, the red line could do that at 4 times the load. I had to slow down the blue line to 1/4 to match that requirement. I can do this even further and say, okay, we met the 99 percentile. Let's say that I also want 99.9 percentile at some other level, like 10 milliseconds or something like that. Shift them both so both of them pass. In this case, I actually slowed down the red line to stay away from the breaking point too. And here I compared looking roughly the same up to the 99.9 percentile. See the difference in throughput? The red line can handle, keeps the same line and better at 10 times the load. Look what I did in the last 2 weeks. I want a bonus. And this is how you ask for a bonus, right? So, you know, we can make this comparison and say we can carry 10 times the load. Now we can do other interesting visuals with this, not just compare two things. We could study the behavior of a system across a spectrum of load. Here's that one system, the worst of the two, at varying loads, different loads. And it's kind of obvious that as you increase the load, you're pushed to the left, right? The interesting thing you get from looking at a set like this is you're seeing kind of the predictable operating range of the system, and you see where it stops being predictable. This line is not in the grouping. It's not yet saturated, but that's 80,000 a second. Remember that don't do this lesson? Don't run there. It's sensitive. You want to be in here. Okay? Now you can choose where you want to be in here, but you kind of have, okay, if it's more or less, it'll move a little. It's not going to collapse all of a sudden. I've established that it's got some operating range where it reacts to the load and shifts the behavior rather than collapse over to 2,000 operations a second. So we could just zoom on that, right? And look at that as the range we're interested in. We could look at the other system and say, oh, it looks like that. We could try to compare them side by side, above each other. There's all kinds of nice visuals you could start doing if you plot a lot of percentile charts in this format. And by the way, all these come out of HDR Histogram with plotting tools that are available online. Here's one of my favorite ways to compare these data sets. We could say, okay, that grouping is system B, that grouping is system A, at similar loads in the groupings. What I can say from here is, see how everything shifts to the right or to the left? At any of these loads, the likelihood of an outlier of a certain size is 100x lower in the better system. Again, a good way to show what is the impact. We did something, we're comparing the two systems. What does the comparison show us? Well, here it is, right? Load, 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 load. They react to load and they vary. Okay. So these are interesting ways to chart things. If you can get your data into these formats, I highly recommend that you start looking at the data. Seeing the visuals teaches you a lot. Once you start looking at these shapes, you start seeing patterns. You start recognizing what things behave like. And, you know, oh, there's a bump, there's two bumps. What does it look like? Maybe that's a GC pause, maybe that's a context switch. I actually look at enough of these that when somebody sends me a J-hiccup chart, I can tell them if it's running on VMware. VMware has a signature that you can see easily in a hiccup chart. It's the only thing I know of that has a perfect 50 millisecond quantum. So when I see quantums that go straight to 50 milliseconds or a mode at 50 milliseconds, I highly suspect VMware. That's the only hypervisor that has that quantum. But that just means I've been looking at way too many charts. Let's go back to the basics. If you don't want to do all the hard stuff, the easiest visual to compare systems with is a maximum plot. Plot the maximum response time in short intervals over time and look at the visual. Not just one system doing stuff, here's another system. One of these looks much better, and it's easy to say, which one of these do you want? Anybody want to guess which one is system A and which one is system B and what we're running here? This is Cassandra. On the left it's running on Hotspot, on the right it's running on Zing. It's very easy to explain with this picture why you want Zing to run your Cassandra workload. Okay. This is why I spend all this time charting. But I learned a lot from doing it, and you can do it for your own systems even if you don't want to buy Zing. So, with this, let's open it up to questions, see what people are interested in challenging. Tell me that this is completely wrong, or that I ruined your life now and you realize everything is terrible. Anyone?
It's question time. Does anybody have any questions to Gil? Come on.
It's easier to measure response time when you have a client and a server, but how to measure response time on just a server? Is it ever possible at all?
It's possible, but it's hard. What I like to say is you can always fix a load generator. And if you want examples of fixed load generators, I've personally, or with colleagues, fixed 3 of them. Anybody here use the WRK load generator for web loads? Work, WRK. It's a common, easy, very good asynchronous load generator. I created WRK2 a couple years ago as a demonstration of here's a wrong way to measure, but it's easy to correct. We fixed Cassandra stress, so the latest release of Cassandra upstream now measures correctly and actually outputs a histogram log that could be plotted this way for service time, wait time, and response time. Of those, the only one you actually care about is response time. But it documents all of them. That's how I got you these pictures of comparing response time and service time. They're straight out of Cassandra stress, the corrected one. And we also fixed YCSB. The interesting thing you can do to fix a load generator, a properly built one at least, is to say load generators have a job to do. They are supposed, when you turn them on, every request they are going to do in the future has a known time. It doesn't mean they have to be at an instant, You could say if it's supposed to do 100 a second, then we can say exactly when every request was supposed to start. If it's supposed to do 100 a second with a Poissonian time distribution, we can still say when every request happened. There's a plan. And if we know what the plan is, then the proper way to measure response time is to say not from when I sent it until when I got the response. That's the service time. It's from when I was supposed to send it until I got the response. If I didn't send it, that's queuing, that's waiting in line. And it's very easy to correct almost any load generator that has some sort of a rate or a plan. The ones that are hard to correct are the ones that do not model a plan, but just make it up as they go. So for example, if somebody says, I want random arrival rates, you can still model that. You could say, before I start, let's plan what random means. Roll the dice a lot of times, say, I will start at this times, now let's go do it. You're still supposed to do that at those times. But most of the load generators that do random simply say, when should I start? Random time in the future, do it. When it comes back, random times in the future, do it. Between them, you're spaced with coordinate omission. Unfortunately, JMeter does that. So you can correct JMeter probably with enough works, but some load generators are easy, and all of them theoretically could be corrected. I just, that's not my job. I've only done 3 of them. Unfortunately, That's good for lab experiments. The real world, we don't have a load generator, we just have the real world, and all we can do is monitor it. And it's really hard to correct monitoring because we don't know what was supposed to happen. We only know what happened. And when we didn't measure, we don't know if people tried or didn't try. And I can't prove that they would have been there. So we could do all kinds of guesswork and filling in the gaps and say, I know I didn't measure for 10 seconds, right? So I know I should have seen at least this. Because outside of that window, this is what happened. Let's project what happened outside into the inside. At that point, you're not doing precise monitoring. You're just filling in the gaps. And you have to decide whether you want to do it conservatively or aggressively, depending on what you want to do. I've built tools that help correct that. HDR Histogram, in fact, has a built-in correction in the API. You could tell it to record a value, or you could tell it to record a value with an expected interval or arrival. And it'll just fill in the gaps. The use for that is, suppose I'm supposed to record something every 1 millisecond, as long as it's less than 1 or 2 milliseconds, that's fine. But if somebody has a 500 millisecond value and the expected interval was 1 millisecond, I know that I had 500 and 499 and 498 and 500 results all the way to 2 milliseconds. I stop at 2x because we don't want to say 1.9 milliseconds also means 0.9 millisecond. I don't know that that would have actually happened. So in HDR Histogram, there's a convenient way to fill in the gaps, but that's a projection. It's not precise, it's not accurate, it's just better than doing nothing. So there are ways to kind of fill those. Hopefully that was a long answer to your question, I think, and unfortunately we don't know what was supposed to happen and we can't measure it easily. Now, what people in practice do is they try and establish a lot of information on what actually happens if they care a lot about latency. So LMAX is one of our customers and partners, and we really like the fact that they will talk about it publicly. We've done talks together about measurement and stuff like that. And a common practice for them is they timestamp things everywhere it goes. So when you put a message in, it records when it was here, when it was here, when it was here for all steps. And they will retain all the data or summarize it correctly and later analyze it. So they don't just say when it arrived or when it exited, they actually measure all the steps in between. Because, okay, something took a long time. What do you do with that? Where did it take a long time? And it is absolutely worth it to add time instrumentation to your code, to your data, to your payloads as they go through your system in order to be able to later go and say, there's a problem, where is the problem? I have a very high 99.9 percentile. Which of these steps was responsible? It's almost impossible to figure that out unless you collected the data at each step in a way that lets you know what the 99.9 percentile of that step is. That means a lot of percentiles, a lot of HDR histograms. That's why they're so fast, to be able to do that. So.
Thank you. The idea is understood.
I think
You guys more questions?
I think we had one in the back there before, I'm not sure who.
So just a quick question, do you use standard deviation at all?
Yes. If you look at the standard way I report percentile distribution, there's actually a text format that I use, and I can read it instead of plot it. At the bottom of it, I always report the min, the max, the average, and the standard deviation. So I always use standard deviation, but I only use it for one purpose, to show that it means nothing. Because what's nice is I look at a lot of this text output. So normally I go, okay, the mean, the max, and the standard deviation. And it's really easy to immediately see that, oh, the max is many standard deviations away from the mean. Yet another wrong data set, right? Or non-normal data set. The only data sets I've ever seen where the standard deviation and the mean and the max live in a common universe that would be normal are ones I generated artificially. There's a histogram There's a histogram generator that you can find on GitHub in my examples directory that makes Poissonian distributions and random distributions and queuing models and stall models, so you can see what the shapes of those are. And those have perfect normal distribution when I'm generating perfect Poissonian, so it works. But the reason I have the number there is to sanity check that it really is wrong, really is wrong. Every time I look at one, I check, yeah, another one that's wrong. And you might actually find one in the real universe where the max is only 10 standard deviations away from the mean or something like that. Okay.
More questions?
If I understood it correctly, does it mean that we really don't need to record the response time in access logs or time to first byte, whatever? Does it make sense to record?
Does it make sense to record time to first byte? Yeah, actually, absolutely, but don't summarize it. Okay? So you want to record it. The best is if you record every single thing. So the time to first byte of every request that you have. You can always analyze that later, right? Don't throw any data. If you have to summarize, because you don't have room for this, it's too much logging, too much data, HDR histogram is really good for aggregating exactly that data. If you have 10,000 of these a second, you don't want 10,000 lines per second in your log, dump it into an HDR histogram and log the HDR histogram itself every second. What will happen is you don't know when in the second that happened, but you know that in that second, this percent was that long. The nice thing in this, and by the way, I didn't explain exactly why this is very important. Histogram logs, which is a format that all the language implementations now support, are built to record a histogram for every interval in time. So rather than percentiles in time, it's the actual histogram that counts at any value. And that's a nice compressed format that's usually a couple hundred bytes per interval. So with a couple of hundred bytes, I can log 1 trillion results that happen in 1 second. It doesn't matter how many results, it's just a distribution. And it compresses very well. The nice behavior of that is what we're logging is a histogram, counts at values. Histograms are additive. If I have the histogram of every second, I could tell you what the histogram for the hour is. I just need to add them all up. I didn't summarize percentiles, so the math is correct. If you want to know what the 99.999 percentile of an hour, add all the histograms in the hour, compute the 99.999% of that histogram, and you have your answer. That's what those plots come from. So the logs that feed that are actually interval logs that have every in second or 5 seconds. Then when we plot them, we do the time span that we're interested in, add them all up and get the distribution. So measure the data, just don't throw it away. Put it in something that will actually let you analyze it later, and that's kind of what we built this for. Okay.
Questions?
Even after your lecture, I believe that we are testing our performance quite okay. I'll explain a bit, and can you criticize or agree? We have SLA for response times, but it's maybe it's not response times, maybe you consider it's a service time. And we have SLA for user load, like 100 users should meet the service SLA, and that loader is doing requests the same way as users will do, wait for response, and only then click next button on the UI. Mm-hmm. So, what can you say about this way of measuring performance?
Do you have a small fixed number of users?
Yeah, 100 number of users.
No, is that your actual world? There are only 100 people that will ever use your system?
No.
Okay. So the reason I ask the question that way, because sometimes that's what you have. It's a departmental application. There are only 50 secretaries using it. That's a different world than it's connected to the web, right? And that needs to handle a certain load. So here is the kind of weakness in a model that does that. You are modeling what a user would do. So you're saying a user would arrive, and if the system stalled for an hour, the user would wait for an hour, but they won't. And during that hour, another user will log in and try, just because your load generator is busy for the next hour, it can't do another user, doesn't mean another user wouldn't have arrived in the real world. I'm intentionally using an hour as an exaggerated time, right? The same applies for 10 seconds or 20 seconds. If your system stalled, I Control-Z'd it for 1 minute.
But if it stalls, it will not meet the SLA of 1 second response time.
1 second response time is the SLA for what? For the maximum?
For user, for every request.
So if any user ever takes longer than 1 second, then it's a failure.
Yep.
Okay. What I like about that is you're measuring the maximum. Right? Only the maximum, and you don't care about anything else. That might work. It's probably too harsh. I mean, honestly, most systems I know would be fine with 1 in 10,000 users seeing more than 1 second. But if you really, if you're willing to say it's broken if anybody ever sees a response longer than 1 second, then you're probably okay because you're not measuring percentiles. The only way you would miss things is after failure, right? So you would already have logged failure. It doesn't matter how much you failed, and you're in a good shape. The systems I usually see that put such a strict SLA are more life and death systems, real-time systems, military systems. But usually when we're dealing with regular enterprise applications, it is okay to have some failure. You just need to say how much. And the problem that happens then is because we're willing to accept some people having more than 1 second, then we don't declare that failure. And then all the measurements start being a problem. So I as far as selling our product, I love systems that say you can never have longer than a second because, all I need is a JVM that pauses for more than 1 second once a year, and I'll sell you a JVM that doesn't, right? But like I said, that's usually more strict than is needed for a lot of systems. And when people try to, you might need a lot more servers to handle your load and meet that, then you need to actually serve your business. If you said, hey, I need 1,000 machines to handle this and make sure it never happens, or 100 machines, one dedicated per user, so I never have that. And then the CFO might say, can you do this a little cheaper? And what if I'm okay with 5 people a day seeing worse than 1 second? Let's do that. At that point, you're starting to ask, when a failure happens, how many times a day I'm allowed, and the failure will hide other failures and you're not counting right. And that's usually when the problems like this start. So specifically for what you described, I think you're okay. It's just, you're probably overestimating the capacity you need.
Okay, thank you.
Thanks.
The last question.
As you shown in your speech, there is actually quite often the problem is what to select, whether it's system A or system B to use. You have to make a choice based on some data. And sometimes you can actually look at the graph and say, here's slope on 99%, here's slope on 99.9. But usually it's quite often when graphs are not very evident, and probably you need some numerical criterion based on your data. And do you have any advices what to use? I guess you will never use student t-test, probably something else.
So, it's a tough question. Like, how do you boil it down to a numerical test? I like to use this format, and let me go back to this one right here. This is just a more abstract format. I like to use this format to define the numerical test I'm looking for. So notice that this doesn't say what percentile. It says these are the requirements, and that step function is a way to say I need that percentile to be better than this, that percentile to be better than that, and so on. So the requirements here are defined at 1, 2, 3 percentiles. You're not saying every percentile what it needs to be, but what you're doing is you're measuring all the percentiles and seeing if they fit inside the requirements. I think this is a valid way to say, am I meeting the stated requirements? I said 3 percentiles need to be at certain levels. This is the part where it's not just the maximum, right? The maximum has to be better than that, but that's a big number. But it's okay for, you know, the 99 point something percentile is there and so on. If you do this, then you're not measuring the percentile of the system against the requirement, you're measuring the requirement against the behavior of the system. Because there's some qualities that are worth mentioning about percentile charts like this. They are monotonic. So they can only grow, right? If you have a percentile at some level, the higher percentiles can only be worse, right? So these are always growing lines. For any percentile, there's an answer of how big it was, right? All the way to, you know, however many nines are in your data. So if you have 1 billion results, we could say what the 9 nines are, right? And by taking this approach, I can avoid the question of, tell me a number that tells me what the performance is, because there is no number, there's a shape, and a number would eliminate the shape. So I try to gravitate towards this, and you can frame that and you can automate that, right? You can collect the data, you can have this data, and you can ask, does these values grow above the requirement line at any point in the chart? And you can just have something that says pass-fail on that. So you can do an automated or numeric test, but it's not a test that says, did some magic number that represents the data set cross some requirement number? It's did it cross at any point during a range that I think is valid. So I'm intentionally avoiding the summary problem in order to look at it as what is your requirement and how are you meeting it, right?
I see, thank you.
By the way, I didn't mention it before, but one of the powerful things about percentiles is they make sense to business people. It's often hard to get these percentiles from business people. But they can think in those terms, and you can make them think in those terms. And I do longer versions of this. I'll do this verbally here. I have this process I call an interview, where you try and get requirements for people, because most of the time, when you go and ask people, you know, we do this all the time. So they say, hey, we have problems, does Zing help? And my answer is not yes, it's what do you need? What are your requirements? And it's very interesting to see this, like, well, I want it to be good. You know, what does good mean to you? So it's outside of the telco industry, it's usually very hard to get actual valid requirements from people. So I've kind of built a process of interviewing a customer, a partner, a friend, myself, to establish SLAs. And you have to play this weird game against yourself. So I usually start off saying, what do you want? Like, what is your requirement? And most people will tell you something like, I'd like the average response to be 20 milliseconds. That's it, that's what they know. They want the average to be good. And I don't like to get into the argument of standard deviations and averages at that point. So I just interpret what they say, and I will say, so you want the common case, most of the results to be around 20 milliseconds, right? That's what you're saying. Because I would probably do that with a median or 90th percentile, and it's probably what they mean. But that's not a requirement on its own. And the next question I'll ask is, so can you tell me what the worst case you're willing to accept is? And usually they'll say, well, we haven't really thought about this. Just don't make it too bad. You know, I don't really have a requirement, just do the other thing. So this is the part where you need to kind of get this out of them, right? And a simple way to do that is to go negative. You say, okay, I'm writing down the requirements. We said you want common case to be 20 milliseconds. Is it okay if the worst case is 5 hours? And at that point, they'll probably say no, unless they're running Hadoop. Then it's okay, but you know, they'll probably say no, no. And so what I would do is say, let me write this down, 20 millisecond common case and no worse than 5 hours. And they'll say, no, it's not what I said, you know? And then they'll give you a number, right? So if it's not what you said, what is it? And they'll say something, 100 milliseconds, don't make worse than 100 milliseconds. And an interesting effect there is they'll usually overreact because you gave them a really bad number, so they give you a really good number and they don't really need it. Say, oh, okay, we can do 100 milliseconds, but you know, like the question that came from here, worst case of 1 second. Well, do you really mean that? What if it happened only 10 times a day? I could do this for $3 million, but if you allow me to fail a little more, I could do it at 1/10 the price. So come on, it won't happen a lot. Right? What's the actual worst case you cannot allow, right? And then they'll back off. They'll think of something that is really bad. In web applications, that might be 10 or 20 seconds. In a system including retries and everything else, failure, whatever it is, right? Or maybe longer, right? So they'll come up with a number. So now I have a couple things. I have a common case and I have a worst case. Without a worst case, usually you can't actually do an SLA thing because, you know, what the engineers will do is they'll move all the outliers there and make them infinite. Now, I have these two numbers, common case, worst case. Those are not enough for an SLA. You need these steps. And the way to get the steps, again, is to ask these annoying questions, right? So you say, so 20 milliseconds common case, 20-second worst case. I'm okay with that. How often am I allowed to do 10 seconds? And at this point, usually the person gets really annoyed because they say, wait a minute, you told me you won't do that a lot. You said no to 100 milliseconds, you won't do that a lot. So and you say, yeah, you're right, but what we have so far written down is the common case, the median, 20 milliseconds. The worst case, 20 seconds. I can build a system that will do half the things in 19.9 seconds and I want my money. Is that okay, right? Half the things take 19.9 seconds. That will meet the requirements we set, and it's probably not what you mean. So tell me how often I'm allowed to do 10 seconds or some other thing. Now, at that point, usually they get it and they start doing things on their own. They'll come up with these percentile levels. They'll say, okay, so the common case is this. Just, you can do this bad, but not more often than this. You could do this bad, but not more often than this, and all the way to the worst. That's how you get these steps. And the actual thing that happens is they'll usually have more steps than needed. They'll give you 5 steps or something. And that's better than 1 step. And over time, you can take away some of the steps because it doesn't matter. By the way, you see this chart? Here's an interesting tip. If you have those lines there that fail, you can spend a lot of time trying to make them fit under the curve. But the first thing you should try and do is go to the guy who gave you that line and say, can I raise that by 40 milliseconds and that by 20 milliseconds and we can all go home? And they'll say, you know what, yeah, that was just a guess. It is so common because, you know, people don't really know what the numbers need to be. They give you estimates, right? The only time you can't move this is when there's a contract in place and you can't move the contract. So the first thing to do is to push back on the requirements. But if you have to do it, then you have to do it. So I told you how to come at that, right? You should think of it from what will happen bad to your business and your system if you don't meet these requirements. And don't be too harsh. Don't say what you wish happened. Say what you're willing to pay for. Now there's an important trick when you're done with this. You will come up with all these percentile steps, because that's easy to think of, and how often are you allowed to, what the likelihood of something would happen. But it'll be a big mistake to just say that's what the percentiles need to be. You need to time bound the percentiles. An actual SLA is those steps, you're not allowed to cross any of them in any 1 hour during the day, or in any 1 minute, or any one day. It's in a time bound. We don't mean that percentile for the year cannot cross this, but it's okay to cross it by a lot between 8 a.m. and 9 a.m. every morning, because the rest of the time it's really good. That's not what we mean. We mean when the system needs to serve its users during a time window that is probably the peak, it still needs to meet its conditions, right? If I fail at peak every day, my average is still good. My percentile for the week, including the 2 weekend days that nobody works, is great. The 99 percentile for a week with 2 idle days is really, really good. But the 99 percentile for the worst half hour of any day is that. So a valid SLA requirement, I would say, is one of these lines that covers everything from 0 to 100% with no gaps. If you put a gap in there, somebody will shoot a percentile straight through the gap, right? And once you do that, say, this needs to happen in the worst period of the day. Worst hour, worst 5 minutes, you'd figure out how long the worst period is. But I need to do this even when things are bad. And now you have something you can test against or monitor against. Now, I keep mentioning this. What will happen if you don't mention the maximums, right? You see this chart? This is real data from a real system, a mature system that was at least 3 years old when I measured it. There's a natural rule for modes of latency of mature systems. You notice something interesting about where the lines bend? They bend at whole numbers of nines. They don't bend between the nines. They bend at 99.9 percentile. And again at 99.99 percentile. Exactly, or very close. Why is that?
SLA? Yeah, because of SLA.
Because engineers were told to do this. Right? There was an SLA and they improved it until they met the SLA. Now guess what the SLA here was? There was an SLA for actually this system has an SLA for the 2 nines and the 4 nines when I met them, but it's very clear somebody was watching the 3 nines and they had no SLA above 4 nines. Nobody said what the max is. The biggest percentile they cared about was 4 nines. Look at the shape of the graph. This is proper engineering. It is. I mean, you were told to meet the 4 nines and then you stop. You sweep everything under the rug and they said it's okay. This is the natural thing that happens to a system when you don't define a good SLA. This is a mature system. It doesn't happen the first time you engineer it because nobody reacted yet. But after it's been working for a while and people improved it, this is what it'll look like if you don't put a cap on that. Now guess what happens when you show the CO this chart? The next day you have a maximum requirement. Because for the first time ever, he saw that his system actually has that number above the 4 nines. He didn't know it was there. Nobody was reporting on it, right? We don't show the maxes. We show the 4 nines because that was the requirement. So it was censored. But when you show people that that happens, they immediately say that can't happen, right? And that's 1,000x as big as the normal. It's not a small number there. So it's an interesting effect of what happens, you know, all this wrongness that happens to us, and when people partly define SLAs and are fuzzy about that, and what we evolve our systems to do. And that's the real world. And this is a trading system. This is not some web system with, you know, and it's really good, actually. They're much, much worse than this.
Okay, I think we have not enough time. Oh, so our time is over. So that's it. Thank you very much.